That song is so familiar. What instrument is that called?
This is my Duduk. This is actually an Armenian instrument dates back to 3,000 years ago.
Oh, that looks so cool. How does the sounds work?
Well, you have different fingerings for this instrument, and each fingering corresponds to a different note.
Oh, that's pretty interesting. I wonder who invented it.
Yeah, me too. I'm also curious how the physics behind this works. It should be related to wavelength and frequencies and how they come together and produce different notes.
Yeah, that's a good question.
You know, I have a friend at McMaster University who's studying physics there, and they're learning about wavelength things. Maybe he could help us.
Okay, do you want to go find him?
Sure.
Yeah, let's go.
Lambda is equal to FC, and I think that works that time.
Look.
He's there, come.
Oh, hey.
Hey Ali, what's up?
Nothing
Are you
much.
busy?
Not really. It's a
Okay.
physics program. There's nothing much to do.
Okay, you're wondering how this wood works. When we change the fingering, we produce different sounds. Such a nice music. Can you explain to us how it works?
No problem. Oh, this is useless. I have a much better idea.
Alright, now we're gonna learn about our instrument from a physical perspective. Okay, so if we look at our instrument, we can see that it is open on both ends. Now, we're gonna assume that it's at the fundamental frequency of n equals 1, at n equals 1. And this is at about a frequency of 440 hertz. Okay, so now if we look at the pipe over here, we can see that it is an open on both sides system as well as having holes at the top. Now what these holes do is expand or contract the size of the length of the actual instrument. So if you plug more holes, the length of the instrument increases, and if you plug less holes, the length of the instrument decreases. Now, we have an example over here. We want to find the wavelength and speed of sound that comes out of playing the note middle C on the Duduk at the fundamental frequency of 440 hertz. The wavelength in our equation is equal to 2L, which is the length, over N, which is the node. And in our case, it's the fundamental frequency, so that equals 1. So if we do the math, our wavelength is equal to 2 times 0.3 meters, because the length is 30 centimeters, over 1, which is equal to a wavelength of 0.6 meters. Now let's calculate our speed. For us, speed is equal to frequency times wavelength. And so that's a frequency at the fundamental frequency of 440 hertz times a wavelength of 0.6 meters. So therefore, that gives us a speed of 264 meters per second.
Now I know how my instrument works. Thank you so much, Ali. Have a good day. See you.
Thank you.